Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it. This is chapter 2.2, which is on polynomial functions of higher degree. All right. So we spoke about quadratics, right? So what we're talking about here is polynomials, right? Like of third degree or higher. All right. So first, let's look at a couple of different facts here. So polynomials are continuous, right? That's a feature in general of polynomials. Not only are they continuous, they have smooth curves, right? So this right here is a polynomial. This has smooth curves. All right. And what we mean by smooth curves is saying this is like a smooth, rounded curve, all right? It doesn't have any abrupt change. For example, if I had something like this, hold on, let me draw that again. If I had something like that, this is not a polynomial. How do I know? Because these curves right here, they're not smooth and rounded. All right, so these corners are not smooth. All right, so that's how I know this isn't a polynomial. Similarly, if I had something like this, let's say I had that, this is not a polynomial. And how do I know that? Well, it's not continuous. It's got this vertical asymptote here, which makes it not continuous. The curves are nice, right? Those are fine. They're smooth, they're rounded, but we have this this vertical asymptote, which makes it not be continuous. All right. So in general, the graph of a polynomial function is going to be a nice smooth curve. All right. Now, let's talk about something called the leading coefficient test. All right. So let f of x be a polynomial function. So a sub n x to the n plus a sub n minus 1 x to the n minus 1, so on and so forth down to a sub 2x squared, a sub 1x, and a naught. All right. So let f of x here a polynomial function. So let that be a polynomial function of degree n. All right, and that has to do with the leading coefficient there. We've got a couple of scenarios, all right, and I will do them this way. So the scenarios are as follows. If n is odd, we're going to have some specific scenarios. And if n is even, we're going to have some other scenarios, right? Not just that, if our leading coefficient, if a sub n is positive, greater than 0, we're going to have some scenarios. And if a sub n, our leading coefficient, is negative, we're going to have different scenarios. Okay, so now, what do we mean here? Well, if n is odd and our leading coefficient is positive, we know right away that our graph is going to start down here and end up here. All right. It doesn't really matter what the inside, what the middle stuff looks like. All right. It can look like a whole bunch of different things here. but the point is that it starts at the bottom left and ends at the top right. All right. Let me move this a little bit and slide that down. What this is really saying is that, and I'm going to be using some fancy terminology here. I'm going to say that this part over here says that as f of x, well, f of x is going to infinity. Let's make a little more space there. There we go. F of x is going to infinity as x goes to infinity, right? As the x values go infinity, the function is going all the way up to positive infinity, upwards. On this side, we're saying that the function is going to negative infinity as x goes to negative infinity. All right, so as the x values go this way, the y values go to the bottom. All right, so that's the behavior happening there. All right. Next scenario. Let's say here we have n being odd. All right, so the degree is odd, but our leading coefficient now is negative. So what that's going to do is it's going to start up here in the second quadrant and end down here in the fourth quadrant. All right. As far as what the inside looks like, it can look like a lot of things. All right. But the point is that this would be a polynomial of an odd degree. In this scenario, in this part here, we're saying that the function goes to infinity as x goes to negative infinity. All right. So as x goes this way, the function goes upwards. On this part over here, we're saying that f of x goes to negative infinity as x goes to positive infinity. There we go. And so as x goes further and further out to the right, the function goes further and further down. All right. Now, next scenario here. When n is even, all right, we have another scenario here. So when n is even and our leading coefficient is positive, so n even, leading coefficient is positive, we have that it starts up here in the second quadrant and ends up here in the first quadrant. All right. And again, what it does in the middle, not so important. It could be something as simple as this. All right. And in here, we would say, well, on this part, f of x is going to infinity as x goes to negative infinity. And on this part, we would say that f of x is going to infinity as x goes to infinity. All right. And lastly, over here, where n is even and our leading coefficient is negative, we would have something like this. We would start at the bottom left quadrant, in other words, the third quadrant, and we would end at the bottom right quadrant, the fourth quadrant. And again, what's going on in the middle, it's not really too important right now. It's just some polynomial of even degree with a negative leading coefficient. In here, we could describe the behavior as the function is going to negative infinity as x goes to negative infinity. And this part, we would say the function is going also to negative infinity as x goes to positive infinity. All right. So in here, we've got the left-hand behavior, the right-hand behavior, left-hand, right-hand, left-hand, right-hand, left-hand, right-hand, right? Because it talks about what's going on over here on the left and over here on the right. All right. So now let's put that to use. Describe the right hand and left hand behavior of each function without graphing. All right, so let's say we had f of x equal to 1/4 x cubed minus 2x. All right, now what we're going to be doing here is we're going to be applying the leading coefficient test. So for the leading coefficient test, well, what do we need? We need to figure out what the leading coefficient is. The leading coefficient is 1/4. Now 1/4, even though it's quite small, it is still greater than 0. In other words, it's a positive leading coefficient. Our degree here is degree 3, right? So here n equals 3. So what does that tell us? Well, we have positive leading coefficient, odd degree. If you recall, that meant that we start at the bottom left and end at the top right. All right, positive leading coefficient of odd degree. So what we're going to say here is that our left-hand behavior is going to say f of x goes to negative infinity as x goes to negative infinity. And our right-hand behavior is that f of x goes to positive infinity as x goes to positive infinity. All right, so as x goes to negative infinity, the function also goes down to negative infinity, left-hand behavior. Over here in the right-hand behavior, as x goes to positive infinity, the function also goes to positive infinity. All right, next one. So b. Let's make that lower. B. There we go. Let's say f of x were equal to 5x cubed minus 3.6x to the fifth, and then that minus 1. All right. So in here, well, again, we're going to be using the leading coefficient test. And for that, we need to figure out, well, what is the leading coefficient? The leading coefficient here is equal to, you would think it's 5, but it's not, because it has to depend on the degree, right? First, let's look at the degree here. What is a degree? It is 5. It's a degree 5. So in here, we're going to be using that. In here, our leading coefficient then has to be attached to our degree. So it is negative 3.6, which is less than 0. And by the way, n equals 5. This is odd, right? So we have an odd degree and a negative leading coefficient. Well, what did that look like? Odd degree, negative leading coefficient. Well, that meant we started up here and we ended down there, right? That's for odd degree, negative leading coefficient. So what we're going to say here is that our left-hand behavior is that f of x goes to not negative infinity. F of x goes to positive infinity right up here, as x goes to negative infinity further to the left. And the right-hand behavior is going to be that the function f of x is going to negative infinity right on the bottom down here, as x goes to positive infinity further out to the right. Next one. So let's say I have f of x is equal to negative 4 plus 5x squared minus x to the 4th. All right. So once again here, we're going to say, well, what is our leading coefficient? What is our degree? All right. So our leading coefficient here is negative 1, which is less than 0, because our degree here is 4, right? So it depends on this term right here. So our leading coefficient is negative 1. Our degree is 4. Now, what does that look like? Well, let's recall. Negative leading coefficient degree 4 means we started at the bottom left and we end at the bottom right. All right. So what we're gonna say is that our left-hand behavior is that f of x goes to negative infinity as x goes to negative infinity, and our right-hand behavior is going to be f of x goes to negative infinity as x goes to positive infinity. All right, so that's the behavior that we get there. All right, so that was using the leading coefficient test. Now let's talk about, well, the leading coefficient test to figure out the behavior. Now let's talk about the real zeros of polynomial functions, right? And in general, anytime we say real in math, we're talking about the real numbers, right? So these are the zeros that are real numbers. So when f is a polynomial function, and a is a real number, the following are equivalent. So what are we talking about here? Well, the first one, so the following statement. So all these following statements are all equivalent. So if I write x equals a, this is a zero of the function f. All right, so this statement is equivalent to saying that x equals a is a solution of the polynomial equation f of x is equal to 0. All right, so saying it is a 0 of the function f is the same thing as saying it is a solution of the polynomial equation f of x equals 0. It is also equivalent to say that the term x minus 3 is a factor of the polynomial f of x. All right, so if x is equal to, well, I don't know why I wrote 3. I should have said x equals x minus a. There we go. I guess anyway, whatever. So if I say x is equal to a, if that's a 0 of a function, I could also say x equals a is a solution of f of x equals 0 of that equation. And I could also say x minus a is a factor of f of x. We can also say that the point a comma 0 is an x-intercept of the graph of f of x. All right, so all of these statements are equivalent. Saying this is 0, it is a solution, that x minus a is a factor, and the point a comma 0 is the x-intercept. Those are all equivalent statements. All right, now I want to make a note here. If f is a polynomial function of degree n, so actually I'm going to make two notes here. So the first note, if f is a polynomial function of degree n, it has at most, so f has at most n real zeros. All right, notice I'm saying at most n real zeros. All right, we'll talk about that a little later. We can also say, or another part here is that the graph of f has at most n minus 1 turns. And in here in parentheses, I'll say this is where the extrema happen. And if you recall the extrema, I'm talking about the relative extrema, the relative max, the relative min, all right? So those happen at the turns, right? So a polynomial function of degree n would have at most n minus 1 turns, all right? So now let's do a quick example here. D. So find all the zeros of f of x is equal to x cubed minus 12x squared plus 32x. All right. So recall that, well, we're finding all the zeros. Finding all the zeros is the same as saying find all the x-intercepts. And the x-intercepts are when y is equal to 0. So what we're going to do here is we're going to say, well, let f of x equal 0. What does that really mean? That means that we have x cubed minus 12x squared plus 32x, and we have that equaling 0. Let's factor out the x. We're left with x squared minus 12x plus 32. And then factoring this out, well, we need two numbers that multiply to 32 but add up to negative 12. Those are negative 4 and negative 8. And set that equal to 0, right? At that point, well, solving this gives us x equals 0, x equals 4, and x equals 8. So we have our three zeros. Our three zeros are 0, 4, and 8. As x-intercepts, we can say that they are 0, 0 from here, 4, 0 from here, and 8, 0 from there. All right. So there we go. Now, notice here that we have a cubic function, right? So this would tell me that at most there's 2 terms, right? We'll talk about that a little bit later. But now, let's talk about repeated zeros. All right. So repeated zeros. So a factor x minus a to the k, where k is greater than 1, yields a repeated zero x equals a of multiplicity k, right? So in here, notice here that k has to be greater than 1. In practice, though, I'm going to be using the or equal to as well, all right? The thing is, strictly by definition, being equal to 1 would not be a repeated zero because it doesn't repeat, right? But we're going to be, when we talk about multiplicity, we're going to be sort of fudging those rules a little bit to allow for x equals 1 to be mentioned in its multiplicity. So now, depending on the multiplicity, we can say a few things. So when k is odd, the graph of x, so the graph crosses the x-axis at a. Maybe I should say at x equals a. All right. Similarly, when k is even, the graph no, it doesn't cross. The graph touches the x-axis but does not cross it, at x equals a. Right? So in other words, it bounces back. So when the multiplicity is odd, it crosses. When the multiplicity is even, it bounces. We're gonna allow, so here, this is really the reason why we're gonna allow k being equal to 1 into the talks of multiplicity, because 1 would be odd, and it's still useful for figuring out what is happening there. So let's see an example. All right. So we're gonna sketch the following. F of x is equal to negative 2x cubed plus 6x squared. All right, and this is how we're gonna do it. First, let's find the multiplicity here. All right. Well, actually, so we need to find the multiplicity of all the zeros. So to do that, we must first find the zeros. So let's find all the zeros. In other words, all the x-intercepts, which is where y is equal to 0. So I'm gonna have negative 2x cubed plus 6x squared, set it equal to 0. Factor out negative 2, and I'm left with, well, actually, no, let's take out a negative 2x squared, and I'm left with an x minus 3 equaling 0. From here, this gives me that x is equal to 0. From here, this gives me that x is equal to 3. But now, what is the multiplicity of them? Well, what we really need to look at here is the exponent. There's a 2 there attached to that x, so this 0 has multiplicity 2. Maybe I'll do it this way. Multiplicity here is equal to 2. The multiplicity for this one is equal to 1 because it's an invisible 1 there, right? And again, technically that's not a multiplicity because it's not a repeated 0, but it is still useful to talk about that. How come? Because what we're going to say here is that since this is odd multiplicity, it's going to cross. And since this is an even multiplicity, it's going to bounce. All right, so let's see. What do we have? We have at 0, at 0, 0, we have a 0, and at 3, 0, we have a 0. Now, what else do we know? Well, from the leading coefficient test, we have an odd polynomial, an odd power polynomial, odd degree. There we go, odd degree, a polynomial of odd degree with a negative leading coefficient, which tells us that we must start up here and end down here. Well, let's figure out what this looks like. Something like this. Here, it's at 0. Remember, it's even multiplicity, so it needs to bounce. It needs to start up here, here, bounce, and then it needs to cross this again. This needs to end down here. All right, and there we go. So that right there is a general sketch of this function. And again, all we did there was we used the multiplicity of the zeros as well as the leading coefficient test. Let's do another one similar to this. So that was E. F. Let's say that we have f of x is equal to 1/4 x to the 4th, negative 1/4 x to the 4th plus 3/2 x to the 3rd, not x to the 5th, x to the 3rd minus 9/4 x squared. All right, so let's see. The very first thing I'm going to do here is I'm going to find the zeros of this, right? So in other words, I'm going to look for all the x-intercepts, which is where y is equal to 0. So I'm going to just go ahead and set this whole thing equal into 0. So negative 1/4 x to the 4th plus 3/2 x cubed minus 9/4 x squared. Set it equal to 0. Next thing I'm going to do here is I want to multiply both sides by negative 4. The reason for that is I want to get rid of this fraction. So if I want to get rid of all the fractions, and I also want to get rid of this negative. So when I multiply everything by negative 4, I end up with x to the 4th minus 6x cubed plus 9x squared is equaling to 0. Factor out x squared times x squared minus 6x plus 9 equals 0. Factor this last part out, x squared times x minus 3 quantity squared, right? Because 3 squared is positive 9 and negative 3 times 2 is negative 6. So in here, I end up with the zeros of x equals 0 and x equals 3. Both of these have multiplicity 2, right? From the exponents. So now we can go ahead and sketch this, because we know from the leading coefficient test that, well, this is even, and so the degree is even and it has a negative leading coefficient, so it must start down here and end down there, right? So let's see, what else do we know? We know we have zeros at 0 as well as at 3, right? And they both have even multiplicity, so they must both bounce. So it starts on here somewhere, hits this, it bounces, and it has to hit this again, so it's got to turn something somewhere, bounce again, and go back down to this. And there you go. That is just a general look of that graph. Next one. Oh, and by the way, notice here that this was 4th degree, and we had 1, 2, 3 turns. So 1 turn, 2 turns, 3 turns. So degree 4, 3 turns. In the previous one, degree 3, 2 turns. 1 turn, 2 turns. All right. All right. Next one, G. Let's say that we have f of x being equal to 2x cubed plus x squared minus 8x minus 4. All right, and again, we want to find the zeros. So to find the zeros, what we really mean is find the x-intercepts, which is where y is equal to 0. So we're going to say that 2x cubed plus x squared minus 8x minus 4 be equal to 0. I'm going to factor this by grouping. From the first two, I see that I can take out an x squared. I'm left with 2x plus 1. From the second two, I can take out a negative 4, and I'm left with 2x plus 1 once again. So what I really have here is 2x plus 1 times x squared minus 4, which really, if I can continue to factor this, I have 2x plus 1 times x plus 2 times x minus 2, giving me all the zeros of negative 1/2, negative 2, and positive 2. All right. In each one of these, the multiplicity is just 1. Right? There's an invisible 1 there in each one of these. So technically, they don't repeat. So what this gives us is, well, that the multiplicity is odd. So we're going to be crossing at each one of those points. So let's say we have at negative 2, we have something happening. At negative 1/2, we have another thing happening. And at 2, we have something else happening. Now, in this specific function, we have something that we hadn't encountered before, and that is a y-intercept that is not just 0. In all the other ones, we had a y-intercept of 0, which is why I didn't even bother to look for it. But in here, we do have a y-intercept. So let's go ahead and find out what that is. And the y-intercept here is when I set this function equaling to 0, right? So the y-intercept is when x equals 0. So when I plug in 0 into the function, sorry. So that gives me f of 0, which is negative 4. So at negative 4, I've got an intercept. And these were at negative 2, negative 1/2, and 2. So now, using the leading coefficient test, I see that I have a 3rd degree polynomial and a positive leading coefficient. So that means that I have odd degree polynomial, means, and with a positive leading coefficient, starts at the bottom left, ends at the top right. So what is it going to look like? Well, they're all odd multiplicities, so it has to cross at every single one of these. It also has to hit this y-intercept. So something like this. All right, and there you go. So that graph looks something like that. All right. Now, let's talk about something called the intermediate value theorem. All right, and we normally abbreviate this IVT. The intermediate value theorem. All right, so let A and B be real numbers such that A is less than B. If f is a polynomial function, if f is a polynomial function such that f of A does not equal to f of B, then in the interval A to B, the open interval A to B, f, and I should say the closed interval, sorry, the closed interval from A to B, f takes every value between f of A and f of B. All right. So let A and B be real numbers such that A is less than B. All right. So what does that mean? Here's A, here's B. A is less than B. All right. If f is a polynomial function, so we're going to be working with a polynomial function, such that f of A is not equal to f of B. So in other words, they're at different heights. So for example, let's say this is the height f of A, and let's say this up here is the height f of B. So f of A does not equal to f of B. They're not the same height. All right. Well, it's saying here that if f is polynomial, then f takes every value between f of A and f of B. So in other words, it's gonna have to hit every single value in here throughout this interval from A to B. So it could look something like this. All right. And there, perhaps I'll make that a little bit more. There you go. All right, so definitely every single value between A and B is hit, right? Excuse me, between f of A and f of B is hit. And in fact, they can even go beyond those. So maybe if I did something like this, they can even go beyond them. But this, the intermediate value theorem, all we're saying is we're guaranteeing that every single value in here is hit. And every single value is hit, right? Some of them multiple times, but every single value there is being hit between A and B. The fact that some of these are beyond that range is okay. Now, so another way of saying this is that, so perhaps I'll do it over here in yellow. Another way of saying this is that there exists a C such that, well, let's do it this way. I'll abbreviate this. There's a C in the interval from A to B such that f of C is, well, let's draw that below it, such that f of C is in the interval between f of A and f of B, whatever that interval may be. Don't worry too much about this notation. I just wanted to show you how to do this in step builder notation or in logical terms. This backwards E is pronounced there exists. Anyway, now how do we use this? All right, so let's do an example. And we're at H. Show that f of x is equal to x cubed minus 3, that's minus 3, x squared minus 2, has a 0 on the interval 3, 4. All right. Show that f of x has a 0 on that interval. All right, so what are we going to do? Well, what we're going to do here is we're going to use the intermediate value theorem. But how? Well, the very first thing we're going to see is, well, what is f of 3? F of 3 is, well, 3 cubed minus 3 times 3 squared minus 2. This is just negative 2. Notice here that this is the same thing as saying 3 cubed. So I have 3 cubed minus 3 cubed goes away. Minus 2 is negative 22. Excuse me, it's negative 2. So that's f of 3. F of 4, well, that would be 4 cubed minus 3 times 4 squared minus 2. And then what would that be? 4 cubed is 64 minus 4 squared is 16. 16 times 3 is 48. And then that minus 2. This is really 64 minus 48 minus 2. That's just 14, positive 14. Now, so what? So what we found here is that, well, a is less than b, right? 3 is less than 4. And f of a is not equal to f of b. Negative 2 is not equal to 14. So the intermediate value theorem applies because we're working with a polynomial, all right? How is that helpful? Well, because we're looking for a 0, and the intermediate value theorem tells us that we have to have every value between negative 2 and 14 being hit. So what we can say is the following. Since f of x is a polynomial, it is continuous, right? And if it is continuous here, we can apply the intermediate value theorem. So we know that f of 3 is equal to negative 2, which is less than 0, and that is less than 14, which is just f of 4. So in other words, we have 0 being between negative 2 and 14. So by the intermediate value theorem, there must exist some c, or a c value, a c, such that c is between 3 and 4, and f of c is equal to 0, all right? Because we have to hit every single height between negative 2 and 14. 0 is between those values. Next one. So semi-static instructions. But now we're gonna say f of x is x to the 4th minus 10x squared plus 3. And we want to show that we have a 0 on the interval from 0 to 1. All right. So how are we going to do this? Well, we're going to do this semi-tag way. What's f of 0? F of 0 is 3, right? This piece goes away, this piece goes away. It's just 3. What's f of 1? Well, f of 1 would be 1 to the 4th, which is 1, minus 10 times 1 squared. 1 squared is 1, so minus 10, and then that plus 3. This gives us negative 6, right? 1 minus 10 is negative 9. Negative 9 plus 3 is negative 6. So what we can say now is that, well, we can apply the intermediate value theorem. So since f of 1, which is negative 6, that's less than 0, and that's less than 3, which is f of 0, right? So negative 6 is less than 3, and 0 is in between them. By the intermediate value theorem, there exists some c, or ac, such that c is between 0 and 1, and f of z is equal to 0. Now, notice here that I'm not, in either of these two examples, that I say what that c value is. We're not asking for that. We're not asking for what that value of c is. We're just saying, just show that it exists. Well, how do we know that it exists? Well, again, in this interval from 0 to 1, I've got some positive values at the beginning, some negative value at the end, so we must have somewhere hit a 0, right? We cannot go from negative 6 all the way to positive 3 without hitting 0. Another way of thinking about this intermediate value theorem is that, like for example, in terms of your height, you don't go from being 4 feet tall to 5 feet tall without having been all the heights in between, right? You would have been 4'1", 4'2", 4'3", so on and so forth, right? You would have hit every single height in between. So that's what this intermediate value theorem is telling us, that if you have a continuous function, in this case a polynomial function, it would include all the values in between between the two, between the two heights. All right, so that right there is where we're gonna end this. So that's the end of 2.2.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.